MHU, magnetic effects of current. So here as you can see I have written magnetic effects of current. Current, what is current? Current is nothing but flow of charges. So it means flow of charges are responsible for creating a magnetic field. Any charge moving creates a magnetic field. Any charge. Moving charge creates a magnetic field. In electrostat, we are familiar that static charge are responsible for electric field. A charge is static, how they interact with other charges. Similarly, here we will see how a moving charge creates a magnetic field. Obviously, moving charge also creates electric field, but it has a wonderful property of creating a magnetic field. A current, which is just flow of charges, produces a magnetic field. So, from various experiments, just you have studied in your earlier classes that when a magnetic needle is placed near a current carrying wire, we observe deflection. It shows a reflection. It means that there is something magnetic property in this current carrying wire which makes this needle to deflect. So this is very basic understanding of how a current carrying wire have a magnetic field around it. So we will have a mathematical formulation for this magnetic field. It is observed that it is proportional to the current I flowing through the wire. It is inversely proportional to the distance at inversely proportional to distance where this is, well, as we increase the distance, intensity of magnetic field will decrease. So we will see this. So the very basic formula which relates the strength of a magnetic field with current and distance is Biot-Savart law. Biot-Savart law. It's very simple law. Let's take a current carrying wire. Current I is flowing through it. We want to calculate a magnetic field at some point P, which is at distance R. Point P as a distance R from an infinitesimal current element dl. Okay. So for this magnetic field produced by this current element at point P is given as nu naught I dl cross R 4 pi R. Nu naught is nothing but nu naught is a magnetic permeability of free space. Mu naught is a magnetic permeability, dl is the infinitesimal current element, R is the distance at which you want to calculate magnetic field, I is the current in the wire. So this is the Biot-Savart law. A lot of questions come from this law. There is application of this law in various. They can give you current loop, any kind of configuration which they can give you and ask you to find a magnetic field. So it's very simple things, but you have to just be aware of how can you utilize this formula in calculating magnetic field. So let's begin with very simple things. Just take an arc. Take an arc which is, let's take it of angle alpha. A current I is flowing in this arc. Now we want to calculate magnetic field at this point P due to this arc, due to this current carrying arc. Okay. So this similarly you have just go process very similar. You have to take a small dl element here and calculate magnetic field due to this element at this point P. Obviously it is an arc, so it's R. Okay. So for this dl element produced by magnetic field produced by this current element at point P is given as dB. dB is nu naught I dl. Obviously this is tangential in a tangent, this is a radial direction which are perpendicular to each other. So dl R sine 90 over 4 pi R cube. This I will cancel, this will turn out to be 1. So we get dB is equal to I dl 4 pi r square. So for this entire arc, magnetic field produced by this entire arc at this point P, we will integrate it dp. You can write dl as some rd alpha. So mu naught I r 4 pi r square r d alpha. So this is cancelled. D is equal to mu naught I by 4 pi r. So we have seen magnetic field produced by this r at point P comes out to be mu naught I alpha 4 pi r. It depends on the angle. You can see it depends on the angle. Angle will increase, means the length of wire will increase, current will increase, and magnetic field will increase. Okay. So let's take a case of a semicircle. For semicircle, alpha is equal to pi. So alpha is equal to pi, magnetic field turns out to be is equal to mu naught 4r. For a circular arc, alpha is equal to 2 pi. So magnetic field will be mu naught I by 2r. So similarly, they can give you any kind of configuration, any kind of angle. Just you have to use this formula. You just replace angle, and you will get the magnetic field produced by that arc at its center. Okay, this is about, we have discussed about some circular things. Let's move toward the current carrying wires. What will the magnetic field produced by a current carrying wire? Okay, we will initially begin with the finite length wire, then we will see for infinite length wire, and later on some more cases. Okay. I'm not supposed to. Okay, let's take a finite wire. And current I is flowing through it, and we want to calculate the magnetic field at point P, which is at distance r. Okay. This end of the wire and this end of the wire make angle alpha and beta respectively. Simply, we will proceed with the same approach. We will take a small infinitesimal small current element dl, and we will calculate the magnetic field produced by this element at point P. Let's take this as a theta. Okay, so dl is equal to L is equal to r tan theta. So dl turns out to be r sec square theta d theta. Similarly, this r we need it. This r is equal to r sec theta. Simply, we know r, we know dl, current I is flowing through it, and we want to just find the magnetic field B. Just do the simple mathematics. I r sec square theta d theta. This is theta, this is 90, this will become 90 plus theta. So the angle between length of the wire and the distance, this vector at which we want to calculate, turns out to be sine 90 plus theta. 4 pi r simplify. So simply dl r sec theta division r sec theta. This will cancel, this will cancel, this will cancel, sec square theta will cancel. So we are left with b is equal to mu naught I 4 pi r. This is cos theta d theta. This is the magnetic field produced by this current element. Now we want field due to this entire wire. So we will integrate over this from minus beta to alpha. B. This thing is constant, take out of the integration. 4 pi r. This is sin theta. This is mu naught I 4 pi r sin alpha plus sin beta. So this here we have the general case for finite length wire. The magnetic field produced by this wire at point P is mu naught I 4 pi sin alpha, and alpha and beta the angles which make alpha is the angle it makes with the upper end of the wire, and beta is the angle it makes with the lower end of the wire. This is very simple case, general case. We can apply this to for just say for infinite length wire. Just take for infinite wire. For infinite wire, alpha is equal to beta is equal to 90 degree. So it will turn out beta is equal to mu naught I by 2 pi r 4 pi r and sin 90 plus sin 90. This is simply 2. So magnetic field by infinite wire turns out to be mu naught I by 2 pi r. Similarly, for let's say for such kind of wire, one end extends to infinity. One end of the wire extends to infinity, and other end is here. For this alpha is equal to 90 and beta is equal to 0. So for this case, magnetic field turns out to be B is equal to mu naught I by 4 pi r. So this is for this case. For infinite case, we have seen B is equal to mu naught I by 2 pi r. This is for infinite. So we have used the application of Biot-Savart law for an arc, for finite length wire, infinite wire. So this law is very useful in calculating the magnetic field at some point. There are other laws, Ampere's law, but we will discuss in some other lecture. So this is very interesting topic to calculate magnetic field and how a moving charge can create a magnetic field. Thanks.